This was the original presentation that I was preparing, and the idea was to make an update on serverless. It's one of those words again that we hear again and again. And actually, I try to take the point of view more of the developer than one of the architects to see what is changing on the development side. How many people here has used serverless technologies such as AWS Lambda or the API Gateway? So, OK, quite a few. I have a few introductory slides, but I will go very quick. So traditionally, we were using virtual machines and installing our own operating system, our software, everything. Containers, they're not really a new technology because probably end of the 90s in BSD, Unix, there was jails, the first kind of container-like experience. Solaris containers were very popular during the second half of the 2000s. But Docker changed the way we manage containers. They provided a very nice interface, especially for developers. It resembles the Git interface somehow, also the concept of the file system. So containers now are very, very popular. And now we have also functions. So the idea of giving to a service provider your code grouped in function, and they will execute it for you, scale it for you, manage it for you. So if you want to start with virtual machines, the idea is that you have images of your virtual machine. On Amazon, we call them the Amazon Machine Imaging, AMI. And you usually run a virtual machine for a few hours or for a few months. It's a disposable architecture, but you can use them for a long period of time. You are in charge of patching of everything that is running on top of the operating system, of the virtual machine, from the operating system to the application. Usually, a single virtual machine is doing a lot of things. You may mix different purposes on a single machine, and you pay per VM and per hour. With containers, you have an image that is much smaller. The container file can be very small because you can build on top of other containers with the Docker file. You use them usually for a shorter period of time, minutes to days. Versioning is embedded in the platform. You usually go single task with a container and then eventually assemble more containers together to build an application. And you still need a virtual machine to run your container on top of. With functions, you only need to provide the code. There is no image. The whole platform is provided by the service. You can run them from microseconds to seconds, usually not a long period of time. Versioning is, again, part of the platform. You go for a very narrow single task for a function. And you pay for memory seconds, so for how much memory you need and for how much time you execute those functions. Usually, with AWS Lambda, you can pay for the hundreds of milliseconds, so very, very granular billing model. And there is a huge free tier with AWS Lambda. So every month, every customer gets 400,000 of gigabyte seconds. That means that if you use function with 1 gigabyte of memory, you have 400,000 of seconds per month for free, all customers, new customer, old customers. If you use less memory, you have more time. So if you use half memory, you have double the time. So you can build a startup and don't pay anything for AWS Lambda. And the idea behind serverless computing is, as our CTO, Werner Vogel, says, is that really no server is easier to manage than no server at all. It's very difficult that people like to manage servers for their own sake. And the idea is, can we extend this concept of serverless to other services? Actually, we already did it. And Amazon S3 is the first service that we launched more than 10 years ago. It was March 2006. And the idea was really to have a storage that is serverless, because you don't need to configure the storage. We will scale it for you, for performance, for provisioning the storage. And this is the same that we are trying to do with AWS Lambda for computing, with the API Gateway for managing your APIs, and so on. The API Gateway in particular is really a nice fit in this story, because it allows you to take Lambda functions or any traditional endpoint available on a virtual machine on EC2 or on another provider. The only important thing is that it is internet reachable. And then you can model your API. your web API, and depending on the request on your web API, you can execute your logic in the backend. We can cache the results if we want to, if you want to optimize, so that you don't need to execute the same function again and again. Usually, an example that I do for caching is if you are a news outlet. So maybe you have an API where you publish news. Of course, the news usually don't change every second. And if there is a big news out, probably a lot of people is going to your API to get the news, so you may want to cache the result. And this is a very enterprisey case study that I want to present. So Tomasz maybe could tell us more enterprise stories on the serverless world. But this is really a story that I like. This is a small media agency in the UK. And they created a website for David Guetta. He was in charge of the anthem for the latest football European Championship. And the idea was that everybody could go online, sing the song together with him, and there could be up to 1 million of people that sing the song, and they were mixed together for the final song that was used for the championship. So everything was built using AWS Lambda and Amazon S3 as storage, so it was completely serverless. I think they gave some numbers, but the final cost of having 1 million of people going online, singing for a short period of time was in the hundreds of dollars, so something really, really, really cheap. And I was always excited by this approach, and that's why when I was asked, I started writing this book. Then now it's still in early access, but it's almost out. I was writing the preface, so the front matter last week, so it should be out by the end of November. And so I was thinking, what do we mean by serverless? Should I bring maybe a better use case to show a serverless architecture? So I think this is the best example of serverless architecture that we can find. This is the London Tube in 1939, and they were counting the number of tickets by hand, so it was completely serverless. To provide the reports to understand which lines were used more and less, where they should provision more infrastructure, less infrastructure. So this is, of course, a joke, but the idea is that there's a lot of discussion around the term serverless. It's not nice to define something as the absence of other things, and you can have this kind of mistakes. So you can rebuild the same in a similar way that we saw this morning, so using IoT to collect information, process the data. But what is really interesting here is not only that you can use a lot of different services, but it's the chain of events that you are moving around here. So there are events triggering other events, so that the logic is not built as a single monolithic application, but is built together with the data flow, with the flow of data. And this is something that we usually are doing in the user interfaces. So I don't know if there are front-end developers here, but in the front end, when you develop a user interface, we are used to have events linked that link to functions. So for example, this is a simple interface. If you create a user, you can have function checking the syntax of the name, of the email, and when you click submit, you launch the information to the backend. So this is an event-driven application for the front end, something that we did for years. And the idea was to have some sort of observers that monitor the targets, in this case the fields, the buttons, and take actions when you click or act on the user interface. Now we are trying to do the same on back-end infrastructure. So we have services, so for example S3 for the storage, DynamoDB for the database, Kinesis for streaming data. And if something is happening here, there's data flowing, a file stored on S3, an item written on the database, you can trigger an action that is a function that can, for example, generate a thumbnail out of a picture or process the streaming data. So the same approach from the front end brought back to the back end. But this is not easy for developers. So if you look at this very complex function here, what do you see? So if you are a backend developer, probably you think in the terms of procedural programming. So you see this is a function. If you are into reactive programming and you're probably working in the front end, you probably say, oh, this is data binding. And it's the same thing that you can interpret in two completely different means. Here you are declaring a function. So if I know the width and the length of a rectangle, I can compute the area. Data binding, the reactive approach, the event-driven approach, is saying, I'm binding these values together. So every time someone is updating this variable, automatically the data that is bound, the area, will be updated. Similar thing as written, but completely different concepts when you put them into place. So this is more the back-end mindset. This is the front-end mindset. We would like to take this mindset and bring it into the back-end development. And event-driven design is the idea that if you have different services, you can chain them together using events, similarly to the examples that we did before. So this means that service A, maybe a customer support service, can trigger service B that can be an email service that will push something to the users. And you can read this as A triggers B, or you can think as a cause effect. So B is being triggered by A, so B is caused by A. And usually our mind is, after millions and millions of years of evolution, we are used to thinking cause and effect. Usually we try to find a cause even if there isn't a cause, because it's how our mind works. And then if you have new services, you can find where they should be triggered. And the idea is that you should ask yourself, this new service that I'm adding, what is the cause that can trigger them? And again, if you add new services, you can think, what is causing E and F? It's C, and then you link them to C by events. And growing on in this way, you can build a complex architecture where the data and the event flow is is moving the logic of the data. And you can also have events going back. So a service at the end can send a notification, an event to a service before, so a cyclic effect. And we will see shortly this can be useful to replace distributed transactions, because usually when you say distributed transaction in an IT conference, the lights go low and everybody's scared because they are very complex and slow. So the idea is that you can have chain of events, and then at the end you can send a notification saying, hey, the chain has been completed and we can move on. And with this approach, each service that builds the application, each function, if we want, in the case of AWS Lambda, has a local visibility. So let's say this is the email service that I was mentioning. It only needs to know who will send events and in which format. What is the internal logic? So if I receive the request to send an email, I need the name and an address, and I should format the email. And who should I notify as output event that I completed my mission, I completed my logic. So all the visibility is local. And when I design and develop this service, I only need to know the interface surrounding the context of the service, the logic inside, but I don't need to know what C, E, F, or even A do. I only need to know the border that is really close to my service. And this is very helpful when you start to have tens or hundreds of services and avoids the complexity of big monoliths. So we are replacing a centralized workflow logic that is typical of very complex large-scale systems with a distributed data flow, where the flow of data and events is defining the logic and how different services are triggered. If we can also see this as an endless debate of choreography versus orchestration, that is another hot topic for developer conferences. Here the idea is, should we have a central rigid orchestration, or we should only give guidelines to the service? So of course we are here, I am proposing the first approach, so giving local visibility to the services and rules so that they can talk to each other without enforcing a central orchestration. But we are still talking of distributed systems. So a lot of things are taken care by AWS Lambda, for example, or the API gateway, but you still should know that there is a distributed architecture. So this is a quite broad topic. So if you are interested, you can look at the presentation from Jonas Bonner. He's the inventor of Akka. He's very active in the reactive community. He's one of the authors of the reactive manifesto. And he says that when you go in a distributed world with microservices, with functions, you get distributed in time and in space. So in space, because of course you have smaller components that you can distribute on different physical systems. In case of a serverless architecture, the provider, Amazon, can do that for you. If you are managing serverless architecture directly with containers, you should manage a lot of those things. And also distributed in time. So time becomes important. So you have concurrency, you have latency. So from the monolith going to the microservices, you have to think of this even if the platform is managing a lot of things for you. And you should definitely avoid having a single database shared by multiple services. Otherwise, they are not independent anymore. You're just writing two functions and deploying them on two different servers. So this is an example that I found on Twitter that I think gives the idea of the problems of having a large database connected to multiple services. And the database, as I said when I was mentioning the distributed transaction, must change, because if you have a lot of smaller database used by this distributed architecture, you cannot go with the old ACID model of atomic, consistent, isolated, and durable transactions, because you have lots of databases, and data must flow across all the databases. So a few years ago, an evolution of this acronym, it's more for fun than for technical reason, but actually it's covering the good attitude that you should have. So the access to data should be associative and commutative, like the addition and multiplication, so that order is not important. So the operation should be as much as possible idempotent. Every time in a distributed architecture, you need to have order assured. That's something that is making things much more complex to scale and to manage. So the distributed architecture means think idempotent, think that things can arrive in any order, and your architecture should be able to manipulate this information. So we go back to the example before. You can replace a distributed transaction by using a chain of events. So each event is bringing the responsibility to other services, and then eventually you can have a final service giving an acknowledgement saying, OK, the old business process that was involving sales, support, whatever has been completed. This is a more practical example. So let's imagine a sort of e-commerce company. So you have a customer service. The customer is created in the customer service. The customer service can go to the catalog and say, hey, show the catalog to this customer. And maybe depending on the customer profile, the catalog can show different costs and different prices because he's a top-level customer. And then if the customer wants to buy, the catalog will go to the payment service and say, hey, this customer wants to buy this product from the catalog. The payment service gets the payment. If it's confirmed, will tell to the order service, hey, OK, this product from the catalog for this customer has been bought, paid, so proceed with to create the order. The order service will ask to the warehouse and say, hey, we need this product. Let's imagine it's a physical product that must be shipped. The warehouse can inform the catalog maybe if the availability of this product has been decreasing, so maybe so that the catalog can notify people there's a few items left. And it will talk to the delivery service for the shipment of the product, and the delivery service will update the order saying, OK, the order has been shipped, the order is in delivery, the order has been delivered and received by the customer. So we are replacing a complex transaction that normally in a monolithic world would be a single database with distributed responsibility, with a chain of events passing the responsibility from one service to the other. And everything can flow, and you have to design a process where the order is really not important. And this is one of the, as I mentioned with Jonas Bonner, the idea of distributed architecture should follow a few patterns. One that is really nice, and I suggest you to read, is the Reactive Manifesto. Has been also updated already, since it's not really new. But the idea is to build applications that are elastic, responsive, and resilient. And all of these come with a serverless platform, because AWS Lambda, for example, can grow and scale for you, manage the availability so that you always have everything back with you. But serverless architecture are not enforcing that the communication between the different services is driven by messages and as much as possible asynchronous. So you can still build synchronous links between functions. Think if you have 10 or 20 functions communicating in a synchronous way, how complex can be. If everything is asynchronous, like in the example that I made before, where everybody is shipping an event and then it's another responsibility to go on. You're not waiting for an acknowledgement at every step. That's the right attitude for the architecture. So all of this to say we need probably to change the way we create application to leverage all the advantage of the serverless world. And we need new architectural patterns. So I'm proposing a few patterns. If you have better idea, tell me so we can fix this or add new other ones. So the first example that we saw with serverless architecture is the web or mobile backend. So the idea is that the user comes with some client application, can be a mobile device or a web application running in the browser. It needs to authenticate, and then the logic is passed to a Lambda function that will expose the functions as the backend API of your application. That then you can use other services like databases or storage. To decouple the architecture a little bit, you can introduce the Amazon API gateway so that you have now not the AWS Lambda API that are, of course, something that is bound to AWS, but you can have a web API. So you are decoupling the implementation with what you expose to the client. And with the Amazon API gateway, you can also use not just Amazon Cognito for authentication, but also open standards like OAuth or JWT. And the same approach could be extended to use WebSockets instead of REST or Web API. So I talked a lot about AWS IoT today. It was not planned when I created this slide. But the idea is that you can use AWS IoT without any device, any physical device at all. You use AWS IoT only for the WebSockets interface. So the client application can have a bidirectional communication because WebSockets are bidirectional. It's not like HTTP that it's a pull request, bidirectional communication. And here the messages are exchanged to Lambda function that can then process the result and send messages back to the client. And you have a very fast bidirectional communication with open standards. If you need to process data, a data stream processing reference architecture can use the different building blocks that we have with Kinesis. So you can stream data to a Kinesis stream and then process the data, in this case, in batch. Kinesis streams is usually a high volume stream processing of records. So you don't want to trigger a function every time a single record comes. But what you can do when you configure a Lambda function, you can say, send me these records in batch of 10, 100, 1,000 records. So a single invocation can process more data, and it's more effective. If you have a lot of data and not a lot of problems with latency, you can use Kinesis firehose. Kinesis firehose will group the data. You say every minute or more. Every time you reach 1 megabyte or more, write the file to a S3 bucket. So Kinesis firehose is buffering the records, and then it's writing big files on S3. And here, of course, you can trigger the new file to launch a Lambda function that will process the whole file when it's there. So it's a little bit slower than this approach, but you have a single function execution for a whole file that can contain hundreds or even millions of records. So if your process is very light, maybe triggering a lot of functions, it's wasting CPU cycles, and this approach can be better. Kinesis Analytics, we saw it briefly, but can be used to improve the data and also to aggregate the data. So sometimes you don't need all the singular records to be processed, but you need maybe the average of the last 5 minutes. If you have a million of records per second, maybe knowing the average every second is enough. So this platform can group the data so that you have millions or maybe of records coming here and just thousands of records going out to the Lambda function to be processed. So it can really make the architecture more effective and less costly. And Kinesis streams can also be used to create a buffered backend. So your client application on your mobile or on your web browser maybe can send information to Kinesis stream so that the Lambda function is not triggered every time a user is clicking, but we receive 100 or 1,000 records at a time, can process this information, and in this scenario can communicate back using SNS mobile push notification. So if this is a mobile application, you get mobile push notification that can be create a sort of bidirectional communication, even if, of course, you can send a lot of them and it's not instantaneous. So if you need bidirectional communication, we can put building blocks together. So we can use the mobile, or now can also be a desktop application, can use AWS IoT using MQTT or WebSockets. And it's buffering the communication to Lambda, and then Lambda can use the communication back of the AWS IoT platform to talk with the device. So this can be very effective if you have a lot of requests. Instead of invoking Lambda every time, you can just buffer, and maybe every 1,000 communication, you can give this back the result. Think of example of a second screen application like televoting, when you need to have maybe a lot of people all in the same minute pushing the button to say, oh, I want to vote for this player, for this, or for. In this case, you have a very narrow peak. This kind of buffering can make the architecture much more effective, and then you need just to give a return status, maybe not every time. And if you want, you can replace Kinesis streams with Kinesis firehose. And the advantage, it's a little bit slower, but for voting application, second screen application can be enough, is that all your customer interaction are stored on S3, because all the communication is stored on S3 and then triggers the Lambda function. This is nice because then you can maybe run your own analytics on those files and understand how users are using your application. It's part of the infrastructure. This is one of the final architecture that you can build. It's quite tricky. I've seen few people doing that, but it's quite interesting. So with Amazon S3, this object storage, you can use website hosting. So you enable the bucket to behave like a website. And you can create routing rules. For example, in case of miss, so if you have a 404, so you go on S3 and there's nothing there, you can have a routing rule that returns like a redirect. So the idea is, let's say that you want to build a dynamic cache of your pictures with different thumbnails of different sizes. The first time, the user will go on the bucket. If the thumbnail that you are asking is not there, the routing rule will redirect the client to make the same request to the Amazon API gateway on some endpoint. This Amazon API gateway can use Lambda to build the thumbnail and can replace the thumbnail and can return back another redirect that will send you here, so you get the thumbnail, and all the next users that will come will find the thumbnail here. So you can create a sort of dynamic cache where when you have a miss, you send the people to the browser, to the API gateway, and then you rebuild the content. The second redirect is not mandatory, but if you need binary data for now, you have to do that. But if the data that you are building is not binary, you can just return it back, and then only the next user will go back to S3. So this is interesting. There is at least one example on GitHub that I found of a company doing that for building all the possible thumbnails. You can also add the S3 lifecycle rules to that. So that means that maybe every 3 months you delete the older pictures. So you create a cache of all the possible thumbnails combination that people is asking. And then after some months, you delete them so that you have a dynamic cache that is adapting to the request from the users. Final 2 examples of architectural patterns are for integration. So the first one is the webhook. This is something 2006 probably. Webhook is a sort of callback for the web. So it's the way you can call from one service another service, and then the service can call you back. And this is very, very easy to implement with the API gateway and a Lambda function. So you can play. We are recently doing an hackathon for chatbots with Slack. And of course, Slack, they support webhooks to talk with their platform. So this is a classical example of what you can do. Another pattern is to integrate new data sources. So I often use DynamoDB as a database example, but maybe you want to use MongoDB or Cassandra. So most of the databases, they have log files because they need some way of replicating the data on another node. So if you create a log monitor that is a software application that is monitoring the log, you can use this log monitor to trigger new events. You can directly invoke Lambda function from this log monitor. Or you can do that using SNS as the trigger. Probably it's better because you can link more function to a single event. Or you can just send all or the right subset of information to Kinesis, where the Lambda function is processing the data and being triggered, so that you have less logic here because you filter the data on AWS Lambda. Or you can use the log monitor to send logs or metrics to CloudWatch, and then CloudWatch can trigger Lambda functions if you want. So in this way, you can, for example, MongoDB has the op log, is a sort of dynamic table where all the information is stored. You can relatively easily write a log monitor for MongoDB that triggers Lambda function when something happens on the database. You don't need to do that on the primary database. You can do that also on a secondary database, on a read replica, for example. And you can use this approach also to extend the functionality of other services that are already there. So for example, I know at least one customer extended X3 to enable auto-compress of object. It's just a Lambda function. Every time something is uploaded on S3, it will get the file, compress it, and add the gzipped version on the same place with the new extension. And the HTTP protocol can also manage that for downloads automatically. You can, a lot of customers sometimes ask for per prefix statistics, so to know the statistics on S3 at folder level, so to know how many files are in a single folder. So you can use the Lambda function that is triggered and keeps some statistics on DynamoDB updated, so that then you can go on DynamoDB and ask how many files, how big are the files in this folder, and find this information. You can use DynamoDB alarms with CloudWatch to enable dynamic scaling. There's at least 2 projects on GitHub to do that. You can extend DynamoDB to support geohashes, like we did this morning in this example. So you, for example, every time a record is written, if there is a latitude and a longitude, the Lambda function can automatically populate the geohash. And then you can use this geohash for lookups on DynamoDB, because it's a single record, so you can do lookups very quickly via geohash. Or you can use this approach to create a generic service discovery platform on AWS. Here you can use CloudWatch events. CloudWatch events is a service that part of CloudWatch that can notify you if a new load balancer has been created, if a new DNS record has been created. And this is usually the link to a new service that is being deployed. So if usually the load balancer is the entry point of a service. So you can have a service discovery tool that every time a new load balancer is created, gets this information and updates a record on a database of your choice, or even on a standard service discovery tool, so that it's automatically managed by events. And the idea is that serverless is really about architecture simplification. And I want to give you an example with one of the standard examples in the serverless world, a media sharing application. So this is the event-driven design, quite abstract from the implementation of a media sharing application. So I have the user is coming with some client application, a mobile device, or a web application. And I want to create a serverless media sharing application similar to Instagram, so when you can upload your pictures and share the pictures with privately or with other people. So the client application, you need to be able to upload the picture, and you can put the metadata together with the picture so that it goes on the repository of the files. And this can trigger a function that will build the thumbnails for displaying this picture on a smaller device. And another event can extract the metadata from the picture and use this metadata that is put by the client application on a database so that the data is indexed and searchable. And then the client can get these pictures to display on the device. And usually when you have this kind of application, you have the list of the latest pictures that has been uploaded. And you don't want to compute that dynamically every time a user is going online. But you can pre-compute that. So every time new metadata is written in the database, you trigger a function that will pre-compute the index for the users that can see this data, and will write it here on the file. And in this way, the client application can download straight from the repository a file with the index of the pictures that have been stored. So in this way, you don't need to go on the database every time you start Instagram, but you go on the database and you download the latest pictures that have been uploaded. And then you can, of course, upload and read the metadata from the database. So this is quite a complex flow that you can build. And then you can start choosing the technology. So for example, if you build it on AWS, you use S3 here. DynamoDB can be a good fit here. Then you have a bunch of Lambda functions to build thumbnails to update the index, extract the metadata. But on some parts, you can start simplifying your architecture because you don't need to build a function to upload content to S3. There is an S3 API to do that. You don't need a function to update the content of the metadata on the database. There's a DynamoDB API to do that. So you start removing functions because you don't need them anymore. Then you can add implementation details, like, OK, for authentication, I want to use Cognito or another service. And then you start to change viewpoint. So for people that is into enterprise architectures, the concept of viewpoint is really important because when an architecture becomes complex, you can't see the whole architecture, all the possible perspective from a single diagram. So frameworks like TOGAF, for example, they explain to you you need to create different viewpoints so that you can see how the architecture behaves on the security side, how it behaves on the technology side, on the business process side. So here we have more on the business process side. We started to put the technology, but we can change and now group the technology together. So all S3 is here, or DynamoDB is here, or Lambda is here. So it's the same architecture. I changed the viewpoint. And now we start to see that we have a put object and a get object from S3. We have a update and get item on DynamoDB, and the function to build thumbnails. And these two functions are triggered by the same event here on S3. So we can chain them together or even replace them with a single function. And then what happens if I want to delete content? In my current model, there is no way to delete the pictures. And if you upload the wrong pictures on Instagram, you want to delete them as quickly as possible. But here you can get help from the REST model because S3 is supporting REST APIs. So you have put, you have get, you also have delete object. And what is nice is that the delete object will trigger another event that this function can manage. So this is an example where you design an architecture, you need to add a new feature, and you find that adding the feature is almost transparent because you just need to add a new access to a new API on S3, and everything is driven by the event itself because you have the delete notification that you need to manage to delete the content from the index. So from 8 functions that were on the first diagram that I showed, with this architecture simplification, now we have 2 functions and 5 native API calls from the service. So we simplified a lot the implementation of this architecture, and this is an example of how you can use serverless to simplify the building of a new application. So serverless architecture is not just for simplifying operations. I don't believe in no ops. So people say with serverless there is no operation. There is still operations. You still need to manage the update, the continuous integration, but it's much simpler. But there are also benefits for developers. So you can use the event-driven design. I gave you a few hints. You can use architectural patterns. Let's build them together. You can integrate new products. I show how to use webhooks or log monitors. Simplify the architecture to use the services, and customize the platform. So if you need auto-compress on S3, you can add a Lambda function and do that. You don't need to wait for us to deploy the new features. So build your application with services, not with servers. This is the right mindset to embrace the serverless architecture. Thank you. Which limit? So the API.
Well, because we exactly tried to implement the AWS Lambda functions, and we found out that after a while, after the certain amount of requests per second, the Lambda was not for us.
But for costs or for?
Yes, for the costs.
So for the cost, of course, I'm a technical person, so I cannot. So the idea here is to understand your business case. And to see how we can solve. Actually, in the example that I show, since this happens sometimes, there were a few examples of using Kinesis as a buffer. And of course, it's a compromise between latency and cost. But if you have the classical example is second screen application where a lot of people is clicking in the same minute, using Kinesis or Kinesis Firehose, can really reduce your cost a lot.
Well, we tried before Kinesis was available, so maybe that was the problem.
But it's also that it's honestly, it's new technology. So there is one of the development framework very popular is called the serverless framework. The version 1.0 was out yesterday. So it's a new word. The idea is let's be here because big customers are using this, not just David Guetta. We have Coca-Cola, we have Thomas Cook. In the UK, we have Travelex that maybe you saw in the currency exchange in the airports. When they needed to launch a new credit card, for them is a pain because every time they launch a new credit card, they have the peak of request, and managing peaks is always complex. So they move everything on AWS Lambda, API Gateway, S3, and I think they spent less than $1,000 for the whole launch of the new credit card, something that for them is usually a big pain to manage because they need to buy new hardware, maybe improve the network connectivity. So this is an example. Also, maybe don't think to change the core of your application as the first serverless project, but think of small projects that can help you understand, play with the technology, and then you can embrace it more broadly.
That is helpful for developers, but what about debugging? How I can debug it easily or run developer environments, for example, my local machine if I need to run them?
So is it possible to run a lot of things locally? There are emulators, or it's very easy to wrap your code to run it locally. I usually don't suggest to do that because it's a distributed world. So normally we are used to have small development environments because production environments are costly. So that's why we develop on our notebook or on the old server of the company. But now with Lambda, you can develop on exactly the same infrastructure, using the same technology, the same latency, the same plus. No, that was the first part. So for development, my suggestion, unless you work on planes or spend hours in the middle of the jungle, use the platform. For debugging, it's a distributed world again, so you can't debug as easy as a single monolithic application. So serverless, in a perspective, is part of microservices. So if you use serverless, you are embracing microservices. So one of the big rules of microservices is add a tracking ID to every request in your log, so that if you have hundreds or tens of services involved in the same transaction, you have the same ID so that you can correlate the logs because they will be distributed. And this is not serverless, it's microservices. And we are trying to enhance this with tools. So CloudWatch Logs is much easier to use now. There are 2 projects on GitHub. One is led by AWS, one is led by a single person that try to create a command line interface where you can search all the logs for a single transaction. If you are interested in some of this, I can send you the link so that you can see that. So I would say on the technology side, we are improving, but it will never be as easy as a single monolithic application because that's why I would say we are in a distributed world here. So you have to embrace the rules of the distributed world. So tracking IDs, having a centralized logs, so this is implemented by the platform. There will be latency. The logs will not be immediately written because it's a distributed world. So it can take a few seconds or a few tens of seconds and under a very high throughput to have the logs consolidated in a central repository. But it's normal. If you need to debug something very quickly, you can bring it locally, but it's something that I would not encourage. Did I answer your question?
So let's thank you.
Thank you.